will be Mike Phillips, who is the Chief Technical Officer at SpeechWorks. He's going to speak to us today about some of their recent work. And before SpeechWorks, Mike was at MIT working with Victor Zhu. And let's see, one of my first exposures to speech recognition was borrowing the acoustic model auditory content from you back in some time ago.
Didn't we work on some little DSP card together? This,
yes.
What was it? I can't remember what this thing was. It plugged into a Spark station.
Yeah,
we did something.
AT&T
Oh,
DSP
God.
board. Anyhow, fortunately, we don't do that anymore. So we'll hear about some more modern work today.
You should say he's a founder of, or he's the founder of SpeechWorks.
One of two. So. Great. Well, it's nice to be here. So I'm pretty much going to give you an overview of sort of what life is like at SpeechWorks doing technology development there, sort of to give you an idea of at least what sort of our view of the state of the art of commercial sort of telephone-based speech deployments are, and also, like I said, to give you sort of I know a lot of you are probably studying this kind of field. You probably might be curious what life is like in companies and the kind of sort of technology topics that we deal with. So I'm going to give you sort of a little overview of what we're doing today, but then spend most of the time on sort of the things that we're currently working on, things that are happening over the next year or so, and even some projections of what happens over the next 3 or 4 years from a technology perspective for speech. So let me start with giving you just a quick company overview. Don't worry, I took out all my marketing slides here, so I had to strip these down for leader, this, you know, that kind of stuff. But, so we were started about 6 years ago, and we recently made this interesting transition from being a private company to a public company about 2 months ago. So that was a lot of fun. We were founded out of, based on technology from MIT. So I worked for many years at MIT, and we licensed that technology and have been commercializing that ever since. I mean, the first couple years was sort of doing the tough but interesting process of taking sort of this pile of research code and turning it into something we could actually sell bits and pieces of. But more recently, we've really been focusing on how we scale this and really make this happen in the marketplace in a fairly wide-scale way. We're now actually, I made the slide about a week ago. It's now about a little over 280, so we'll be close to 300 people soon. We have offices scattered all over the place. We actually have salespeople all over the place. These are actually offices where there's people doing real work. Oh, I can't say that when there's the salespeople in the room, but the real work of actually doing development and so on. So in New York, we got about, our main office is in Boston. We got about 15 people in New York, about 15 in San Francisco, almost 30 in Montreal, and then some international offices. And this is because we're doing more languages, more sort of adapting to local markets. And we really need people in the markets for doing that. So we have one office in Mexico, one in Singapore, and one in London. And we're focused completely on, we actually used to call this telephone-based speech sort of products, tools, and services. We now sort of call this network-based because we think over time the way you use these systems is not just telephones, but all sorts of random devices. We'll talk about that later on, where primarily this network is the telephone network right now, but will change over time. And when I say products, tools, and services, we don't just sell sort of technology embodied in products. We also have a lot of tools that are required to actually build real applications. And probably even more interesting, and this is actually one of the things that we've specialized in a lot as a company versus some of the other companies out there, is we have around 100 people who all they do is build applications or work with other partners to help build applications. So they're sort of specializing in the technology and programming and worrying about user interface issues and so on across a wide range of applications. And this is really important right now in the current sort of state of this sort of marketplace. I mean, if you look back 20 years ago when people were trying to do, I don't even know how many years ago, sometime in the past, if you wanted to do a database application, there weren't that many people in the world that knew how to take some piece of software from Oracle or somebody and build a database application. But now, of course, there's a whole industry of people that know how to do database programming. And we're very much in this early stage in this speech market. There's not a lot of people out there that know how to take this technology and build useful applications out of it. So we're sort of filling in that area by having a lot of people that know how to do that. So sorry, these are not meant to be marketing slides. I just want to give you an idea that there is a lot of sort of customers out there for this now. In fact, this slide's a bit old too. I mean, what we saw like 2 or 3 years ago was what's sort of considered early adopter market activity for technology, meaning only sort of the daring few companies that were sort of willing to go out on a limb would take this kind of technology and build an application. And those first ones are really in the couple industries like the online brokerage firms, companies like E-Trade and Charles Schwab and whatnot had these things out 2 or 3 years ago. And some of the airlines were starting to do some internal things a couple of years ago. But what's interesting recently, and this is really sort of spreading across all sorts of markets now, where it's becoming fairly accepted, at least in some of these areas, that it makes sense to have a speech system answering the telephone to do something or another for you. I mean, it's still not quite the default. We think one day it'll be the default. If you have a touch-tone system, you're going to be considered sort of very old-fashioned somehow, one of these things where you push buttons. But for a lot of new systems these days, it's becoming fairly accepted that you would use a speech system for doing some new service versus a touch-tone system. And I guess just as another sort of indicator of what's going on out there, I don't know if any of you have been hearing about this. There's this new notion of a voice portal, right? So you call 1-800-44-ANITA, for example, is one of the voice portals that we work with. And you've got this one number that lets you do all sorts of things, like get weather, get sports scores, get stock quotes, and whatnot. There's about 50 companies out there that are building voice portals, which is just kind of incredible. I think that's way too many, frankly. And that's just for one sort of application that suddenly there's this huge amount of activity and a huge amount of financing to companies willing to go off and build these sort of applications. So that's a sort of another indication that this, over the last year or so, we've really progressed in terms of sort of market acceptance of these kind of systems. So enough with that. Let me tell you a little bit just the current state of what these systems end up looking like. I mean, this is sort of the stack of things necessary to build these things. Down at the very bottom is the core technologies that you guys all know something about. And the main technologies we use are 3 things: automatic speech recognition, ASR, TTS, which is the output side, text-to-speech, and speaker verification. And we could build the applications directly out of these core technologies, and this is what we used to do. But it was a lot of work. I mean, handling all the sort of low-level user interface details we used to have to do with the core technologies. We've since built a couple other layers. There's a layer we have called dialogue modules, which are really just sort of software objects that handle low-level interface details. And then these things usually live in some sort of application development environment, usually supplied not by us, but by the guys that make the actual boxes that these things run in. Some of them are these little drag and drop GUI things where you put a little block on the screen that answers the phone, and then you drag another one to play a prompt and another one to do this or that. The idea is you should be able to build these applications without even knowing how to program. And it turns out not to be quite right, because actually the dragging boxes on the screen ends up being programming after all anyway. So you end up having to have programmers that learn this sort of funny graphical thing. But I mean, this is sort of the current state of how you build these kind of systems. I can sort of skip through this. I mean, this is sort of the state of what these speech recognizers do these days. Continuous speaker independent speech is obviously important. I assume you guys all know this. I mean, phonetic means that we're doing all this with phonetic modeling. You can add new words easily. You don't have to train it to each individual word. Bargain, this is the ability to interrupt the outgoing speech of the system. It turns out to be a bit challenging because the signal coming back from networks includes not only the user's speech, but an echoed version of the outgoing speech of the system. So we have to do this thing called adaptive echo cancellation. It turns out to be tricky in various ways. Sort of vocabulary size, if that's any decent measure, which actually I don't think is a very good measure anymore of how difficult these tasks are. But we're deploying systems now with 70,000 word vocabularies. We're doing one with about 100,000 word vocabulary. And that seems to be doable now, for these sort of telephone-based systems. We use this word natural language. I don't know how many of you are familiar with like the DARPA communicator work, where they're really trying to build completely conversational systems that can understand basically anything you might say in a given domain. We're not going nearly to that extent in commercial systems yet, but we are sort of using natural language processing to allow experienced users to sort of shortcut through a lot of detail steps. I mean, if you call one of our systems, like if you call United Airlines flight information, that's one of our systems, where it's basically prompting you for each piece of information at a time. What's your destination city? Boston, where you're going from, San Francisco. But in some of those systems, actually not that one I don't think, but in some of these systems we're starting to make it so users, even though it's being prompted for in a very machine-directed way, users can actually say things. When it's asking where do you want to go from, you could say from Boston to Denver next Tuesday, and then it won't ask you for the other things. So that's sort of the current state of natural language processing for these things. Dynamic vocabularies and grammars, this is a big change from what we used to be able to do in the research world, where a lot of applications require the actual vocabulary of the system to change dynamically on the fly. Based on some previous information in the conversation, we now have to suddenly recognize some new set of words we never knew about before. And we're doing this stuff in lots of different languages. Let me just say a few words about this next layer, this dialogue modules. Really the reason for this, as I said, was to sort of handle the low-level user interface details that we were seeing over and over again. So, just to give you an idea, just to collect one piece of information from the user, what's the name of the airport you want to travel to or something like that. We have to handle all the things that might happen. If we're just building a demo, which we used to build easily, a little demo, you could make it so as long as you did the right thing, everything worked properly. But in real life, you have to handle anything that might happen. So, what might happen, the user might not speak anything. Okay, in which case you want to give the user another prompt that maybe is a little bit more helpful this time because maybe they didn't say anything because they didn't understand the question. And, the second and third time through, you want a more and more detailed prompt. And likewise, if they said something that you don't understand, you want to come back and say, sorry, I didn't understand you. And again, more and more detailed prompts over time. Confidence interpretation. This means if the machine is very sure about the thing, it should just go ahead and proceed. If it's not so sure, maybe it should come back and say, I think you said Boston, is that correct? Yeah, yes or no. And as much as we love speech recognition, we've got to handle touch-tone input simultaneously. It makes sense for something like an account number, right? You're sitting in, you're driving in your car, you want to speak your account number in your PIN. If you're sitting in your cube with your neighbors nearby, you want to type it in. And even if we're asking a question that doesn't have, it's not necessarily sensible that someone would type something in, they may type something anyway, and we've got to handle it in some reasonable fashion. We have to do something called disambiguation. We might, there's 3 airports in the New York City area, which one do you mean? And this make use of previous information. If you have this dialogue, I think you said Boston, is that correct? No, Austin. If the machine comes back again and says, I think you said Boston, is that correct? People get very mad and hang up on it. So you really have to take into account at least some local sort of context information. So these dialogue modules, as I say, are sort of software objects that handle all these low-level user interface details. And they've made a big difference in terms of sort of making it easier to build these systems and sort of lowering the bar in terms of expertise. A lot of times people are trying to use this technology to build systems, and these people doing it may know how to build a system where you push the buttons, and to translate that into a decent speech system is actually pretty hard. Let me mention a few things about what we do in this solutions group. Remember, I told you we have about 100 people that go off and build speech applications. And the way we used to do it, we used to have a small team of experts that would sort of sit down together and do whatever it took to get a particular application working and working well. Clearly, that's not scalable. We're hiring lots of people to do lots of application development. So we pushed pretty hard internally to have a pretty well-defined process that we go through to build an application. So let me just take you through that real quickly. And the primary part of this, and I'm not going to go through all these things, but the primary issue that we found, in fact, sort of the biggest determiner of success of these systems is sort of less on the technology these days and much more on this thing we call the user interface. And by the user interface, we mean what is the structure of the flow of the application? What is the details of the prompts that are being spoken? How does the system sort of keep things on track? In fact, we have about 20 people who specialize just in speech user interface design. So we actually spend a lot of time.
Is that the technical background, or are they? So like when we were at
we actually hired a linguist to do this sort of thing.
When we were at IBM, we were burdened by all these human factors people who were experts in human, got PhDs in human factors, etc. These seemed thought that they were pretty useless. So what's your, they were going to run tests and blah, blah, blah.
Well, it is those same sort of people. They come from a bunch of different backgrounds. Some of them are linguists looking for a more lucrative way to spend their careers. Some of them are psychologists. Some of them come from human-computer interface. But, first of all, we don't hire people with PhDs in this. We tend to hire people who have at least some inclination and interest in interface. And then we train them heavily in the speech aspect of it. We have a couple guys that are really sort of leaders in this and sort of lead that group, pushing them as to sort of the appropriate methods for it. Yeah, in fact, at what is that? The HCI, I'm blanking on the name. There's a whole conference on human-computer interface topics. Kai, that's what I'm thinking. Yeah, Kai. I mean, there is an emerging field of people specializing in this speech interface aspects, and you know, there are a lot of competing theories out there of it. And maybe I'll take you through just a few things that we're finding to be very important, sort of less theoretical issues and more sort of process issues. And one of them is before you can design what the user interface is going to be, you really have to understand the problem, understand sort of the needs both of the person who's buying the system from us. We call it the service provider, the person deploying the system. You need to understand what they're trying to achieve, but also you really need to understand the callers. We do a lot of interviewing of callers. We do a lot of looking at existing touchtone patterns because you're trying to figure out what are they trying to achieve, what do they know, and then you're trying to design the best way for them to achieve the thing they're trying to achieve. So we can do this early on, maybe do a little testing at this phase, but not very much. And we usually get it pretty much right, at least within a certain class of applications with a certain style of interaction. And then, like I said, I'm not going to go through all this. The main point is when we're actually developing the system, we actually iterate the thing with something in the middle called usability testing, where we actually bring people in. We have a little room with a one-way mirror and a camera and whatnot. I mean, you don't really need all that, but be able to actually watch people trying to interact with the system, where we give them tasks, right? I mean, we learned earlier on that the person's trying to deploy the system to let people access their banking accounts. So we bring people in and say, here, access your banking account, and we see whether they could do it or not. And you learn a lot, and we end up changing things as we're doing this. And then even more importantly, and this is actually tough at first to get customers to be willing to do, and that is even as we're deploying the system, we're still changing it. So because this usability testing wasn't real people. It was people we brought in and paid them $5 or whatever to try to accomplish some task. You learn certain things, but then what you really want to learn is when you actually deploy it for the real customers somehow, we actually can still tune the thing. And, we're doing sort of recognition things. We're tuning pronunciations. We're tuning grammars and vocabularies. We're tuning language models and acoustic models. But we're also tuning the prompts in the system. We're tuning some structure in the user interface. And I didn't go into this in detail, but all these things I've been going through, we've been trying to make easier and easier over time. So for example, one of the big technology things we've done over the last couple of years is to make this tuning of pronunciations, language models, and acoustic models very easy. In fact, we're doing unsupervised adaptation of all three of those things now so that we can do it quickly and easily at a low cost. Sorry?
Is the tuning done in a manual way or is it automatic?
Well, as I was just mentioning, these three we can now do unsupervised. So it's completely automatic. Tuning up grammars, we don't know how to detect out of vocabulary and change grammars automatically. And the other thing we don't know how to do automatically is actually changing the user interface and the prompting and whatnot. But I mean, these things turn out to be extremely important. I mean, we can take systems that entering this phase have something like 80% transaction completion rate, which is something we measure. What percentage of the users trying to accomplish the task actually end up finishing it? We can start at 80% coming into this process and be at 96 or 97 coming out of it. Okay. And the other thing we built, and I mentioned earlier on, is a big set of tools to allow you to do this easier, right? I mean, you need to be able to go in and look in detail at what's happening as people are interacting with the system. So, the system's running, it logs data, and then we can look at it in various kinds of ways, including be able to recreate phone calls. Turns out to be the simplest and most useful tool of all is based on an event log and based on potentially recordings of the user's speech. We can actually pretty much recreate exactly what happened in the phone call, and going in and looking at that is a key piece of actually tuning these things up. Okay. I'm sorry, if this stuff seems not terribly interesting from a technical standpoint, but this is absolutely key to getting these things working well, and something that's been largely ignored until recently. Let me switch to a completely separate topic now, which is another sort of current thing that's happening that some of you guys may have heard about. And that is a lot of the applications we're starting to build are people building telephone interfaces to mimic something that they're already supplying on the web, right? They're already doing flight information on the web, they want a speech version of that. They're already doing stock quotes on the web, they want a speech version of that. And in this notion, we really want the users to feel like they're interacting with the same application just through two different modalities. Turns out that the way we've been doing this up till now is build a completely separate application on the speech thing because it lives on some specialized, what we call IVR platform, a specialized box for doing an application, which is living completely separate from the web application. Not so great, but doable. There's a big movement afoot, not just from us, but from the entire industry, to try to make use of the web programming methods, web programming model for speech applications. And that basically means that instead of having these speech applications living in some specialized language on a telephony box, have the application actually live out on a web server, and then generate some sort of markup to XML markup to control the telephony resources, the speech recognition resources. In fact, there's a big thing underway called Voice XML for doing this. There's a consortium, W3C. We're all involved in trying to define a new language for speech applications called Voice XML. Just to give you the picture of that, I mean, I suppose it should be obvious. Rather than the applications living on these telephony boxes, they live out here and communicate through Voice XML. And whether this is the internet or some well-managed private network, which is probably what you'd like if you're a big company doing this, it doesn't matter so much. The point is the sort of using the web programming model for doing these things. So, that was sort of the current situation. It was a very quick view of the current situation. Now I want to give you an idea of sort of some of the core technology things that we're doing. Is that fine? Is there any questions yet so far? Okay. Let me, I'm going to fly through a couple different topics. One is on speech recognition. We still certainly see, and I'm glad to see there's lots of people still doing research here on speech recognition. We certainly see there's fundamental issues yet to be solved with ASR. This is just meant to be a sort of a glimpse of the sort of things we're doing over the next year or so. I've got slides on the first few, I think on all of them, so let me just go quickly through them. Very large vocabulary. I told you we were deploying systems up to now that have vocabulary sizes up to maybe 70,000 words. I mean, by vocabulary size, I mean that's sort of the active list of words that can be listened for at any point in time in some grammar. We were just recently adopted the FSM or FST technology from AT&T. I think some of you guys here know all about that, so I probably don't need to go into too much detail. But it's basically allowing us to now handle much larger vocabularies, and we're testing vocabularies up to about 1 million words right now. We can probably go farther than that if we need to. And the real key to get us there was less computation and memory for any particular size vocabulary. I'm going to skip the demos, but this really enables sort of a certain set of new applications. So things like directory assistance, things like searching for a book on Amazon or something like that is something we can now handle from at least a search complexity standpoint. This has been a pretty interesting set of functionality that we just got from them. The other thing, we're doing a lot of sort of core technology pieces around sort of the support for this voice XML because well, and also these voice portals that want to have applications that go off and do all sorts of different things. It's putting some new demands on the speech technology. So for example, we now need very fully dynamic grammars because you can expect, these voice XML notions. You want to have a box that can take an application from any sort of web server out there and be able to quickly configure itself to run that thing. So we need to be able to take grammars on the fly, convert them into what the recognizer needs, and run those things very quickly. So we're actually making use of FSTs and keeping things not quite composed until the last minute. It's been a big gain for doing those things. Parallel grammars, there's notions in voice XML that you need to be able to run multiple grammars in parallel such that someone can say something out of any of these different pages and have something happen. So that's putting a new strain on speech recognizers. Dramatic memory footprint reduction, this is something that we're getting also out of the FSTs. This is, some of these guys now are wanting to run 1,000 different applications on 1,000 boxes, but they want any of the 1,000 applications to be able to run on any of the 1,000 boxes. So we've got a lot of sort of, we need the ability to have very low resource usage across a wide range of applications and grammars on these things. And there's a notion of we're trying to embed more sort of computation ability actually in the grammars to do sort of dynamic semantic constructs within the grammars, and we're actually embedding JavaScript. This is also coming out of the voice XML. This robustness and accuracy, I mean, what we're finding, and this is perhaps an interesting topic to talk to you guys more about, is we're getting to the point where for most applications, the actual speech recognition technology is working well enough. I mean, in many of these cases, if we cut the error rate by a factor of 2 for a given application, most users would not notice. However, in all these cases, it's still very easy to break these things. And to us, this notion that it's very easy to break them still, we throw into this lump that we call robustness. And the kind of work that we're doing is to try to look at all the different things that break our systems, break speech recognizers, and categorize them, okay? Impulse noise, loud background noise, cellular conditions, foreign accents, speaking styles. And then for each of these sort of significant cases that are causing problems, we're doing special work to try to improve those things. And obviously, if we can come up with techniques that help a whole bunch of cases, that's a good thing, too. And in fact, the one that we're spending the most time on right now is that wireless environments are becoming increasingly important. I mean, basically, the network in which we're operating has been degrading over the last couple of years, and it's continuing to degrade. It used to be all wireline calls. Now there's all sorts of cellular calls. There's all sorts of voice over IP is starting to be an issue. There's basically a lot more variability in the kind of signal that we see now than it was even 2 years ago. So we're doing quite a bit of work there now, and we've gotten some pretty significant performance improvements, at least for the major cases of what we're seeing in wireless, but there's a lot more to be done there. Let me mention natural language for a few minutes, because I already talked a while ago about that most of these systems are fairly what we would call a system-directed dialogue, where the system is asking you, either telling you explicitly what your choices are, you can choose one of these 5 things, or asking you a question that we're pretty sure we're going to know how you're going to respond to that. But we're trying to incorporate more natural language, not to enable a conversational system like the DARPA communicator guys are trying to do, but rather to enable experienced users very rapid ways to do the 5 things that they do all the time for some given system as there's more and more repeat usage. And we can do that today, but it's pretty hard with our current tools and our current technology. So we have a whole group in New York that's working on improved tools for these things. So things like being able to take existing bits and pieces of grammars that some expert wrote and be able to incorporate them in very nice ways and mix and match them. This wildcards in grammars means that rather than having to explicitly model all the things that a person might say, we can leave things open. Obviously, though, to the degree you can model what people really say, you can improve performance, but we want to have the ability to escape out of that, so we're doing that. Remember, we talked about these dialogue modules that handle sort of nice little chunks of functionality. Well, what happens if you want to put sort of natural language commands, be able to say, transfer $200 from my checking account to my savings account, any place in an application? We're now building the ability to have those sort of things run in parallel with the other sort of structured part of the applications that you're building. And we're also now starting to work on our own high-level application framework to make it easier to build applications. So far, we've worked by taking our technology and stuffing it into the machines that were built for the touchtone systems. And that's okay, and that's been important from a sort of marketing standpoint, because those are sort of our primary sales channels. But these things are obviously not ideal for building speech applications. So we're starting to now get around that by building some other sort of application frameworks ourselves that really make use of natural language processing. We also think there's an interesting notion of being able to even push things up to a higher level, to make very high-level objects that are very reusable. I mean, there's things we do in applications that we do over and over again. Things like navigating through a list of items in a controlled way, or searching through an item based on a set of attributes. I mean, looking for a restaurant or looking for a movie theater. In some ways, those are very similar actions, and we can build very high-level constructs to allow you to do that in an easy way. And there's another notion of a big problem with using natural language processing is how do the users know how they're supposed to interact with these things? And we think there's hope over time that if we are careful in how we build these things, that users can learn one system and make use of certain things they've learned from this system on some other system. So things like knowing that if a system is going to ask me 5 pieces of information in a certain order, that I should be able to say those things in random orders and have the machine respond to it. Now, people are only going to learn that if there's some consistency across applications to let them do this over and over again. Otherwise, we're going to have to learn it for every single application out there. So we're trying to push this notion of common user interface constructs. And in fact, there's some standards bodies that are trying to do this as standards. It's not going to happen by a standards body. It's going to happen by making the tools such that it's very easy to build these things and hoping people adopt those things and do it over and over again. And finally, there's another one that we're adopting from AT&T called How May I Help You, which I have a slide on. I don't know, did any of you already, do you all already know about this, or is this a new topic for you?
Warren was here several years ago.
Okay, so the work of Al Goren at AT&T, let me just reiterate for those of you who didn't see him a couple of years ago, is the kind of applications we've been tackling so far are really pretty structured interactions. Booking an airline flight, the system knows it needs these 5 pieces of information from you to book an airline flight. So it makes sense to have a machine-directed dialogue to handle this thing. There's another class of applications that just don't fit that model. And the general class are where what the user knows, what they have in their head, they can't map onto any given structure we might provide. So you're calling Dell Computer because when you insert this floppy disk, the screen turns blue. If it's press 1 for software, press 2 for hardware, there's no button on there for pressing this 87 when your screen goes blue when you insert your floppy disk. And you can't map this thing onto the structure that you might provide. So, in fact, I think I have a demo of this. This is perhaps a slightly optimistic demo because this is Al Goren's voice. You always know that this is a suspicious demo when it's Al Goren's voice, but this stuff really does work.
How may I help you?
Yeah, I was talking to my brother when we were disconnected.
What was the number that you dialed?
It was area code 301-555-1234.
Was the call billed to the phone that you're calling from now?
Yes, it was.
I've given you credit for that call. Thank you for using AT&T.
Like I said,
going to connect him, or is just going to give him credit?
giving him credit. So in fact, that's...
I want to continue talking to my brother.
Well, that particular interaction was to handle the case where the person made a phone call that didn't work and they needed credit for it. And that's, by the way, the other reason you couldn't do this with a, press 5 for a billing credit. People would say, yeah, I want one of those, right? So, like I said, I think that's a slightly optimistic use of this technology. However, there's been a lot of work being done, and it looks to us like this technology is possible to be used to automate at least a certain percentage of this type of call, and we're actually beginning to do that. I actually have a few slides of how this works. I mean, it's a pretty intensive process to build these things because we actually have to first put out a simulated system and collect a large amount of data, probably 10 or 20,000 utterances of people interacting with actually a simulated system. We can't just do human-human recordings because people will talk to the human differently than talk to the person. So we collect a lot of data, we annotate it, so we get our poor transcribers to transcribe these 20,000 utterances as to which sort of topic it was. And then we with some statistical techniques that are automatically finding sort of what are, they call them salient phrases, which sort of bits and pieces out of these sentences actually were important for the meaning, and then how much each of these things was actually related to the topic that you're doing. So like I said, some fairly well-defined statistical techniques that for doing this kind of mapping this is sort of an example for this, where long distance call could easily map into any 3 of these things, but then the charge my home phone number didn't map into any of these 2 things very well and had a much higher score for the credit thing, the charge thing. And again, this is all learned during this training phase. There's also a dialogue component where charging my home number, so we get the meaning, but there's more information we need. We need to know which number do you want to call and your home phone number. So there's a fairly well-defined structure for doing this, and we're actually starting to roll out these systems for a couple of customers right now. But they're, like I say, it's a fairly, we're adding yet another sort of step of work to deploying these things because now we do have this big simulation phase compared to these sort of previous style systems where we could decide, here is the user interface, here is the grammars, we're going to make users conform to it. But it does open up a new set of applications that are becoming pretty important. I mean, doing something like help desk for a computer manufacturer is a huge expense for those guys. So even if you can only automate 20 or 30% of the calls, it's a big, big win for them. So we're doing that. The other thing that's becoming increasingly important, in fact, we were not working on until 3 months ago, was text-to-speech. And by the way, I guess I didn't mention, we recently signed a technology licensing deal with AT&T. We've been doing our own technology development based on the stuff from MIT, and we have about 30 people doing technology development. But then we came on this opportunity to actually license a big chunk of technology from AT&T. So we're sort of in a big process of digesting it all right now. So two of those things were that. And text-to-speech is the other one, where ability to generate output on the fly is more important. I mean, what we used to do, and we still do for most applications, is get high-quality human recordings as the system voice, and either play them back as whole pieces, or if we have to play back something like a flight schedule or a stock quote, we chop up little bits and pieces and we paste it back together again with all sorts of specialized code for doing that. And that's actually what people want for most of these applications. They really want high-quality voice for these things. But there's applications that you just can't do that, right? If there's dynamic information, that's changing all the time, like a news story or emails or something like this, or these voice portals are driving up a lot of demand for these things, where they want access over the speech to all sorts of stuff out there on the web, or if you're doing a very large vocabulary task. Now we're doing this, 500,000 word recognition task. How are we going to ever record all the prompts so we can come back and say, I think you said, whatever name of some book, is that what you meant? And the other thing is that the quality suddenly seems to be getting into the realm of acceptable. And I just have a few examples of this, where this is sort of the state of the art as of about a year ago.
Welcome to the United Airlines Flight Information System. Flight 695 leaves Boston at 2:35 p.m. and arrives in Denver at 6:22 p.m.
And then this is a product that we just released a couple weeks ago, which was based on this technology we got out of AT&T.
Welcome to the United Airlines Flight Information System. Flight 695 leaves Boston at 2:35 p.m. and arrives in Denver at 6:22 p.m.
And the basic approach to this technology is to do a large amount of recordings from a given person. So a person spoke something like 10 or 20 hours of speech. And that was actually true in the previous case. This Lucent text-to-speech was called diphone-based concatenation, where you record a small amount of speech and chop out little, what's called a diphone, half of one phone up to the next half of the other for every possible pair of phonemes. The newer approach, though, instead of deciding ahead of time exactly what units you're going to paste together for any given sentence, you record a whole bunch of speech, you label it carefully according to the phonetic units and the prosodics of that corpus. And then for any given sentence that you want to generate, the system actually searches through all the different units it has in this big corpus of speech and tries to find the ones to paste together that best matches, A, what you want, right? So you get the sort of the words and the prosodics you want, but more importantly, hooks together in the best possible way. So there's a lot of constraints in there for how these things actually go together to sound quite natural.
Could we hear Festival and LNH?
Sure. Festival is actually, Festival is actually a research system that was one of the first of this large corpus unit selection-based approaches.
From where?
This is Alan Black and Paul Taylor. In fact, it says so.
This is a short introduction to the Festival speech synthesis system. Festival was developed by Alan Black and Paul Taylor at the Center for Speech Technology Research, University of Edinburgh.
So again, I think that's actually a slightly optimistic version, because you can tune these things up and make them sound quite good. All the rest on here were just things that I typed into a website, so they're not tuned up. Festival is a research system. In fact, there's a lot of interesting research going on by these guys, Alan Black and now Kevin Lenzo at Carnegie Mellon University. LNH RealSpeak was the first commercial product that made use of this approach.
Welcome to the United Airlines Flight Information System. Flight 235 leaves Boston at 2:32 p.m. and arrives in Denver at 6:34 p.m.
So pretty good. And as you see, these things still are not perfect.
Is it fair to compare the two? I
Yeah,
mean,
sure.
LNH and Speechify female, of course, the Speechify
Yeah.
female
Here, let me-
is better, but
Oh.
did you do something special to it, or is it a fair comparison?
I did not do anything special. And the other thing is to let you know is there's customers are doing their own evaluations and choosing. In fact, Yahoo today just went live with a email reading service using Speechify female voice. So the evaluations are that people are preferring that. I mean, we're still doing a lot of work. I mean, we're doing things like increasing the density of these things so you can cram lots and lots of channels into a box and more operating systems. There's a big issue of creating new voices. So we're going to be adding a lot of new voices for this sort of thing, and also doing custom voices for customers. It turns out to be important, right? You know, if Yahoo has that voice, their Yahoo competitor is not going to be real happy to have their email reader with the same voice. That's going to be a big issue. And the other is, in this kind of approach, there's a lot of potential, and this is what I'm particularly excited about. If we do some amount of application-specific tuning, we can really boost up the quality of these things. So imagine, you know, we have this 10 hours of speech that's generic across domains. Just adding 1 or 2 hours of speech for a given domain, like a flight reservations or weather information, will boost the quality quite a significant amount. And we're also doing new languages. Sorry, so this is a little bit more, you know, where we think things are going on core technologies. And well, one way to predict the future is just look at the past and assume the same trends will hold. So this has actually been, maybe this isn't so important to you guys, but this is having a big impact as to what it actually costs to deploy these things. I mean, we're now to the point where we can, you know, in a given box, where a box is, you know, in fact, the box that this is measured from is a little 2U rack mount thing from Intel that Intel sells for a couple $1,000s with a dual 700 megahertz processor. We can support 120 simultaneous speech recognition sessions on such a box at a cost of, you know, around $100 per simultaneous session right now. So it's really gotten to the point where the actual hardware cost of these things is almost insignificant compared to all the other costs involved. And this was not the case a couple of years ago. It used to be a pretty big expense to actually try to deploy these things, and this is having a big effect. Of course, if you project that out, we're going to be running, you know, 800 channels of speech recognition on for $10 a port or something like that. But and actually, that's probably not what we're going to do. But actually, what this means for you guys is how do we use more processing to improve speech recognition? We can afford to use more processing now than, or we will be able to afford to use more processing than we are right now. So in fact, some of the kinds of things that we're doing in speech recognition are, the other thing I do mention is we have lots and lots of training data now. So we're doing things like what happens if we do quinphone models, you know, context-dependent models with 2 on each side, and train up 10,000 of these things and run those instead of, you know, 2,000 triphones or something like that. But I think there's a lot of work that can be done on, supposing you take off some constraints on computation, supposing you have lots and lots of training data, what things can you do to make speech recognition better? In fact, if you look at accuracy, and this is we've been measuring internally that we've been cutting error rates on sort of product-related things that we've been measuring at about 15% every 3 months, 15% relative error rate reduction. And some of that's from better technology, but a lot of it's also coming from faster processors and more training data. Nonetheless, if these trends continue, I think. But you know, we're already doing quite well. I mean, things like digit strings. This is on real data. Digit strings, you know, we're below 5% error on a continuous digit string. And what that really means, actually, is in clean conditions, we're at about 1 or 2% string error rate for a digit string.
So that was much better. I thought that AT&T, you know, maybe it's only under research conditions, but
Yep.
they had this enormous amount of data on which they trained, and that it was less than 1%. And
String or digit per digit?
I thought string, but maybe I'm wrong.
Well, I know what AT&T does. So there's a big dependence on what data you test on. And this is actually testing on real data from people calling into these systems. And most of the remaining errors are strong accents, very bad noise or channel conditions, very fast speaking rates. These are, we're getting to the point where it's mainly pathological cases. Unfortunately, there's a lot of pathological cases out there.
You know, when I'm in Europe and call United States, that's done by speech recognition. I mean, you say digits. I usually put pauses in,
Right.
you know, between
No
digits,
need.
and then it does, you know. I don't know how well I don't even dare to put continuous speech in,
Right.
but when I speak the way I want to, I've described, then it almost never makes any error.
You know, this is the experience, you know, a lot of us internally use these systems all the time, and they basically never make errors on people speaking in a very relatively clean.
So it's probably,
Right.
so I have a little bit more of it. I'm a little more reticent to feeding it.
And I mean, the other thing we're doing, obviously, is we're adding harder and harder tasks. We're doing, how do we recognize a name out of 100,000? How do we recognize an email address? In fact, how are we using this continued sort of progress on the core technology? And I mean, I really think that for a lot of our applications, cutting error rate in factor of 2, you're not going to notice. If you took our United Airlines flight information, cut error rate, 1 out of 100 person or 2 out of 100 people will notice a difference, but most people won't notice a difference. Jack?
On your previous slide on those simple tasks, do you know if there's a large difference or what sort of difference there is between when people know it's a man-machine transaction versus when they think it's human-to-human?
I don't know, because I think users of these systems always know that they're, or at least the systems that we've deployed, they always know that they're talking to a machine.
So you'd expect the rates to be better then?
I would guess. I would guess that if you're trying to measure, trying to do similar tasks on human-human interactions, it would be a lot worse, would be my guess. So if my hypothesis is true, and that is, cutting error rates by a factor of 2 on a given application, you wouldn't notice, why are we still investing lots and lots of money and effort in this? And it's because we want to support more and more difficult tasks, and we want to do things like recognizing an email address over the phone or a very large name list and whatnot. And furthermore, and this is probably more important, is to be able to support richer and richer user interfaces. To really open up the floodgates and the sort of things that you can say here will improve things a lot. So.
Well, really, how may I help you would really be the most
right.
what one would want, right? Because it's just terrible when you call somebody and they give you this long menu and you have to wait.
Right.
And you think it's probably this one, but you have to wait till the end in case there's something more precise that
So I think there's plenty of potential for improving these systems over the next 5 and 10 and whatnot years by improving core technology, allowing us to do more and more flexible user interfaces.
I have a question.
Yeah, sure. Go ahead.
Which is sort of psychological. Do you understand why you call somebody up and they want to say your social security number? So you tell them the social security number, then finally a person comes on and asks you for your social security number. Why is this?
So it turns out that...
Is it because do they in fact ask for information which they never use, or they just don't know how to deploy it?
It's not that they don't know how. It turns out that the infrastructure, there'll be some vast call center that they've invested, tens or hundreds of millions of dollars in that infrastructure. Phones now come in, and there's something in the network that's doing the initial question, and they don't have a way, just infrastructure-wise, to get what this system over here knows onto the screen of the operator. I mean, there's a whole field out there called CTI, computer telemetry.
So do you, in fact, are you engaged in putting things on the screen of the operator also, or only?
When possible, right? So we like situations where we can do that, but a lot of places where that's an obvious thing to do, they don't have the infrastructure yet that allows them to do that. I mean, the whole telephony infrastructure world is a sort of in many cases, it's a big mess to actually get that kind of thing working within a call center. Yes, Jack?
So, distinguishing now between raw technology, whatever that means, and core technology, are you in fact making these 15% gains every 3 months by changing the core technology, or are these mostly constraint changes in application builds? And I mean, honestly, what is the main path of progress for making those kinds of improvements?
So those numbers that I mentioned, the 15% every 3 months, are on the same test set. So it's, the same utterances we know, and they're big test sets, so we really trust these numbers. So we're not changing the test, we're not changing the user interface, we're not changing the application. We're changing the technology, and we're adding training data. And we are adding potentially more computation because we can change our thresholds.
I'm interested in the distinction between core technology and other.
Yeah, we don't separate out. We don't separate out, at least in these kind of tests, we don't separate out the changes to technology and the effect of adding more training data or the effect of changing our computation thresholds. So I don't have that separate. I suspect it's probably half and half. Probably half sort of real progress on the technology, and the other half is we're just gaining by being there, basically. So natural language, as Fred mentioned, this is becoming an increasingly important thing to have a really nice interface for people. And in fact, though, I don't think we're currently so much limited by this from the technology perspective. I think we're much more limited by what users expect. I mean, if we try to deploy a DARPA-style conversational interface for a flight reservation system, I don't think our users would like it, because we get constant feedback from the users that they actually like having the system guide them through the interaction, which is kind of the sort of the opposite of what people are trying to achieve from a technology perspective right now. So, I mean, I think there is a current sort of, in fact, here I show you the current state of the art, we believe, in a user interface is sort of a mix of what we call directed dialogue or machine-directed dialogue, plus this notion of natural language shortcuts to allow the experienced users to learn faster ways to navigate through, which is a very different goal than trying to make a conversational system. Plus this notion that we think is really important, although hard to achieve in the real world, called personalization, meaning the system should know something about you, Fred, and knowing that you're calling up this flight travel system, and here's where you live, and here's where you typically travel. I should be able to make the user interface much better for you. I mean, just simple things like if it's the first time calling, we should give fairly helpful long prompts so you know what in the world to do. But if you've called 3 times this week, you probably don't need the long helpful prompts. We can shorten the interaction. So, there's a lot that can be done to make the user interaction better if you know who's calling and know something about them. But really what we're doing is we're sort of driving a set of tools based on what we think is the current state of the art of systems. So in fact, the current goal of the tool development we're doing is this second bullet here, how to make it easier to build those systems. But then what we think happens is as users gain experience using these types of systems, we can then evolve the user interface. Because I mean, the current situation is someone calls one of our systems. We have to assume they've never called a speech system on the telephone before, or at least it's likely. So in the first 10 or 15 seconds, we basically have to explain to them what they're supposed to do. And that's not an easy task. It really does limit the user interface a lot. But hopefully we can make use of previous experience and start to use that in the interfaces and evolve the user interfaces, and then we evolve the tools to try to match that. We also I've been mentioning the DARPA Communicator project. We just started participating again in the DARPA research world, and we're really starting to compare sort of the state of the art of these more natural language systems with these more directed dialogue systems, and we're learning a lot of interesting things. TTS, let me just sort of fly through the rest of these, and we're going to continue to increase the quality. I think within the next couple of years, we're going to be able to approach sort of human quality, at least within specific application domains. I think that's pretty exciting. Back to this notion, maybe you guys don't care about this so much. There's this notion of voice XML that we talked about earlier. But there's also, this is causing this notion, and I don't know whether it's realistic or not, that speech over these various interfaces is going to end up being just like the web, right? Where you can go from, you've got your browser, you can go from one application to another, you've got search engines, you've got portals, you've got sort of the entire infrastructure that you currently have on the web, you're going to have through voice over the telephone. And at least one of the assumptions is that voice XML is going to be the driver for that. Once there's a standard language for applications, you can have these browsers out there that can just sort of point to any application and access them over the telephone. We actually think that that's a tough notion to achieve because there's going to be some big interoperability problems for these various speech browsers. The details of speech recognition are a lot harder to reconcile than the details of how to put a picture up on your web browser. We're pushing to try to engage in this and try to make this happen better. We're actually doing an open source browser effort to try to increase sort of the interoperability out there. And of course, the behind the scenes thing is then sell more product underneath to do those things. And we also have the notion of something we call speech links, which is the ability to go from one application to another by actually redirecting the voice path with a data handshake versus this voice XML notion. Sorry.
So this is still doing recognition on the server side, not on the client side?
Well, it depends on what you mean by the client and the server. Just to be clear, there's a box that has telephony stuff in it. Speech recognition lives there along with the voice XML interpreter. Applications then live out on things that are essentially web servers where they running the application, generating markup for the telephony box. And whether you call one the server or a client, people get it each way.
Yeah, I was actually thinking like maybe you have the recognition on my PC, and then you give it to what is the application. And
Well, that's a separate notion actually being pursued by some people out there, which is basically speech enabling your local web browser so that you don't have to type. But it's a completely different topic than what I'm talking about here. So, we're sort of doing ongoing development within this notion of trying to create a sort of open web of these speech applications, whether caller patterns really change. I mean, the current way that you use the telephone is you have a given number for a given service that you want to call, and you dial that number and you do a thing. Whether that pattern of usage changes from, instead of that, you go to something like a My Yahoo or a My Lycos, the telephone version, and use that to do all your telephone stuff. I don't really know, but we're trying to make sure that we're well equipped in either case. There are some other interesting things that are happening in the actual phone network itself that, right now the phone network is called circuit switch. This is the normal public switch telephone network, where it's starting to change to more of a data network. The voice over IP means transmit voice over a data network. And so we're starting to play within that environment. Cellular is starting to become more and more of a factor, as I mentioned already. And the other thing that's happening that's affecting our lives is increased mobile use of these systems. And really, actually, the primary factor there is less sort of the networking issues and more sort of environmental noise, and people are even trying to do these things hands-free in cars right now. And this is certainly adding some challenges to speech recognition that we're spending time with. Just to give you another view, I mean, as this network changes, sorry, this is the overall picture for these things, where speech recognizer and our software lives in these telephony boxes. Those hook off to some applications or databases. And then through the telephone network, there's a phone out on the other end. So one thing, like, when that network changes to the voice over IP, which is starting to happen, what changes? Well, one view of this picture is not much changes. I mean, the hardware in this box is a little bit different now, but this picture pretty much stays the same. Where it gets interesting, though, is once this becomes a data network, the devices out at the edge of the network can become all sorts of more interesting devices other than just telephones. In fact, I've got a slide on that in just 1 minute, so let's hold that for a second. We're also looking at sort of, just skip forward, this notion of distributed speech recognition. One thing that happens is if the devices on the edge are computing devices and the network is now a data network versus a voice network, we could actually put the front end of the speech recognizer out on the device. In fact, Hinek Hermansky has been very involved in this. Is he around? He's going to be coming later on or something? So there's a lot of work being done on trying to figure out what is the right sort of front-end features you might compute on a device and then send over a network to a network-based speech recognizer. And there's some good reasons for doing that. You can do adaptive noise cancellation at the edge of the network instead of in the network. It makes a lot of sense. You can do sort of these acoustic echo cancellation. You can actually afford to do that out at the edge. And you can do a sort of better job of sending the trade-off between performance and bandwidth. You can pick a better point if the bits that you're sending over the network are bits especially designed for speech recognizer versus bits that are designed for someone speaking. So you can improve performance quite a bit. So the final thing I wanted to discuss is, like I say, most of our devices that we're working with right now are telephones, but now there's starting to be all sorts of interesting devices. So this is just one example. This is the compact iPac that has, a microphone, it has a speaker, it has a high-resolution display, it has wireless networking if you can plug in the right card to it. And there's an increasing use of those things. And by the way, cell phones are coming out that's from the other direction, that cell phones are starting to have displays and browsers and whatnot in them. So what does this mean? I think one thing that's interesting from a speech interface perspective is having the display has ramifications on what the user interface is like. Because now you can start to show users where they are in a dialogue, you can show them what their choices are, and you can give back information like lists and maps and things like that. You can also, where we've got the wireless networking, obviously too small for a keyboard. So speech as an input modality makes a lot of sense for these things, and also pointing may make sense. So in fact, an interesting research topic for us right now is how those two things combine, and speech and display out, obviously. Oops, sorry. Yeah. So we're actually starting to do work now on this sort of mobile computing devices that have displays to sort of investigate, not so much yet the commercial appeal of those things. So I think it's still a little bit too early. There's not enough of them out there for an AOL or someone like that to be willing to build their service to work especially with these things. But in the next 2 or 3 years, that's likely to be the case. So we're starting to put a lot of effort into understanding this from a technology perspective and a user interface perspective. So, summary. I mean, people actually were asking us a couple of years ago, okay, with the internet, or now when these phones have little internet browsers in it, why are you guys going to need to exist anymore? And we think that's absolutely not the right view. We think, speech is becoming sort of a UI of choice, or user interface of choice, at least, especially within the mobile environments. I mean, I think if you're sitting there at your desk, so to answer your question about people trying to speech enable their desktop PC web browser, I actually don't find that compelling because the keyboard and mouse are not that bad to use for your desktop. But with increasing sort of use of mobile computing, this is becoming a very important modality for these things. And the sort of things that we're doing to try to sort of make this very ubiquitous and very far-ranging is obviously continued progress in core technology, I think, is important. This evolution of speech user interface, I actually think is probably the most important thing, and sort of the most important factor that's going to either cause this to sort of spread very rapidly to lots of markets and be viewed as very successful, or there's still a danger of it being viewed as a bad thing from users, that, oh, here's one of these speech systems I have to battle with again. If the user interface is not right, people are going to start to feel that. We're sort of making a lot of use of platforms now that are sort of optimized for speech. It's becoming a lot sort of less expensive to deploy these things than it was a while back. And the sort of evolution of standards will certainly have an impact on how fast we do this. So, that's all I had. So I don't know if you have some time for questions. Pardon me? I actually think that that's a good thing to add to these things. I mean, especially for desktop. I mean, I think eventually the computer should have a camera to not only read lips, but the other thing is to know when you're talking to it, right? I mean, this is a big problem actually when people have tried to use speech processing for desktop applications. Is if you have the microphone listening all the time, it picks up all sorts of garbage. If you have to push the button to talk to it, why don't you just push the button to do the thing? So if it had a camera so it knew that when you were talking to it, I think that would solve that problem, along with lip reading would improve performance of speech recognition.
One of your first slides, you talked about supervised adaptation for the acoustic models and pronunciation. Do they all work about equally well? Or are you finding that unsupervised adaptation for all those tasks works well in others?
Yeah, and we're finding that unsupervised adaptation for those things works almost as well as the supervised version. Just to make sure everyone's clear, by unsupervised we mean, well, supervised means that we took a lot of speech, a human transcriber would label that they said this word, we then feed that into the training algorithms. Unsupervised is get rid of the step of having the human listen to it and see what was said. And by doing unsupervised, we can now make it a very easy automated process to train these things. And we're finding about the same performance with unsupervised as we get with supervised, at least certainly for acoustic model training and language model training. Now realize that we have, and we pay a lot of attention to the confidence scores coming out of the speech recognizer. We also have, remember, these dialogue modules that built in is a confirmation step potentially. So we have low confidence utterances where the user confirmed, yes, this is what I want, or no, this is not, and we can actually use that for the unsupervised training. So I guess it's not completely unsupervised because the user is doing some of the supervision for us.
You mentioned grammars throughout your talk. What sort of grammars do you mean? Regular grammars?
Yeah, I mean, currently we're using fairly simple grammars expressed through a BNS, a finite state grammars. But we are now incorporating the ability to do these FSM. So we have a lot more flexibility now with tools for generating statistical grammars, variable length n-grams and things like this. But so far these have been, like I say, fairly simplistic grammars where, again, for an application where the machine is driving the interaction and asking pretty well-defined questions, we pretty much can by hand decide what the grammar is going to be of what the user should be allowed to speak back. And versus, and this is how we help you, there's no way you can get away with that. You have to do a statistical grammar of some sort for a much more open-ended task, or that's our impression anyway.
how deep would that sort of seems like go? I mean, you gotta call it to, want to find out which was the most powerful earthquake or basic question. Will it answer or say?
Well, which? Sorry.
How may I help you?
Well, within a particular domain, so if you train it to a particular domain, it should be able to answer questions within that domain. Now, a related question, though, is how wide a domain is doable with that technology, and we don't know the answer to that yet. Clearly, we can use this for doing, a person calling a bank and wanting 5 departments within the bank. It seems to work for that. And I suspect we cannot use it for an unconstrained search of information on the internet. But I don't know where the boundaries are in between there.
Do you think a computer situation like that is feasible? Like you call computer
For an automated helpline for a computer, it's certainly possible to automate a certain percentage of the calls. I don't know what that percentage is. I suspect it's more than 20 or 30% and less than 70 or 80%. But even if you can automate 20 or 30%, this turns out to be pretty interesting for people, especially if you can capture the speech and use it for the humans later on.
Well, thank you very much.
Thanks.